Hey guys, I just figured some of these questions are pretty hard. It might be useful for me to go over them. So here we are. I'll show you the strategy to find them. I won't necessarily get to the final answer if it involves a calculator because I don't have one on me, but you've got the answers attached. Yeah, so it's more about finding the process of finding the answer. Most of these I can do in my head anyway. You would probably want to fast forward to the section of the video you're actually interested in because it might be a little long. All right, let's do it. So first guy, we got this object going 5 meters per second, goes off a 10-meter roof. And we want to know the time between the object leaving the roof and hitting the ground. Big key sort of understanding thing you should note is we don't care about this because horizontal components have no effect on vertical components. If something is going 500 meters per second horizontally and has no like wing effect or anything like that, it'll take just as long to fall as if you just dropped it. So we're just going to consider this guy to be dropping. Drop 10 meters. By the way, for these AP physics questions, it's set up so you can just assume that the acceleration of gravity is 10 meters per second squared instead of 9.8 meters per second squared. And that will make a lot of the questions work out nicely. So I'm just going to use D equals VIT, and I'm going to use 0 for VI because there is no vertical displacement. And remember, you never want to mix vertical and horizontal components. So I'm just going to say it's equal to VIT, but my VI is 0 vertically plus 1/2 AT squared. So my displacement, by the way, I'm making down positive just to make everything delightful. So it went down 10 meters and it's accelerating at 10 meters per second squared, T squared. So really, I can cancel out my 10s, multiply both sides by 2, and basically T just equals root 2. Once you're done all this, do a little algebra on this guy and it'll come right out. So that's how you do that sucker. Number 2, so we got this car X starts out really fast right at the beginning. I guess it was zooming right to the starting line and the other one had to hit the gas when the start happened. But car Y has a bigger max speed, so it gets going faster. Car X just has its constant speed it was going. Anyway, so we want to know what is true at time 20. And keep in mind, area under a graph is displacement. So these guys are not passing each other at this point because car Y has a much bigger area under the graph, or twice the area under the graph, in fact. However, they're going the same speed at that point. Car Y has not gone as far, so car Y is behind car X. So that's this guy. Car Y is certainly not passing car X because they'd have to be at the same position at that point. That'll come up, don't worry. Car Y is certainly not in front of car X. It hasn't gone as far. This area is less than this area. They certainly do not have the same acceleration. Car X has 0 acceleration and car Y is rocketing pretty good. And car X is not accelerating faster than car Y. It's accelerating at 0. It's got a slope of 0. A derivative, a velocity derivative of 0, rate of change. All right, and then from time 0 to time 40, both areas under the curves are equal. Therefore, they're at the same position. They're the same distance from the starting line, which means car Y is passing car X because they're at the same point, but car Y is faster and continuing to get faster still. So it's going twice as fast at this point. So your answer is this guy. Because right here, both areas under the graphs are equal. And car Y is going a heck of a lot faster. All right, this guy is a little killer because you gotta separate out the distance it goes in the first second and the distance it goes in the last 10 seconds. So basically break it up from 0 to 1. So D from 0 to 1 second. It's just going a constant speed of 24 meters per second. So it just went 24 meters in the first second. And then For the next bit, it's already going 24 meters per second, but now it's slowing down, or it's accelerating backwards in the negative direction at 6 meters per second squared. So your next 10 seconds from 1 to 11, it's going to be, we're just going to use VIT plus 1/2 AT squared. So we got VIT plus 1/2 AT squared. VI is 24. It started off going 24 meters per second forward, and it did so. Our time is 10 seconds from 1 to 11. 1/2 -6. Don't forget that negative, because this is opposite that direction. These need to have opposite signs. And then times 10 squared. So we've got right here, 1/2 times -6 is -3 times 10 squared. 10 squared is 100. -3 times 10 squared. So we got -300 here. And then we got 240. So we've got -60 for the displacement from 1 to 11. But we had that 24 we did in the first second. So it's basically our D total is equal to our displacement in the first second, or displacement in the last 10 seconds. So 24 plus -60, which would be -36. Ta-da! And away we go. All right. So for this guy, we want an object uniformly accelerated from rest. So it starts off at 0, and it's uniformly accelerated, so the speed is going up by a certain amount each time. So it should be something like, should have a speed graph kind of like this. And if we look at that, that leaves A and E. And E is our go-to, because if it started at rest and it's getting faster and faster, our displacement should be getting bigger and bigger. Also notice that our speed is going up and up and up, and this is the slope of this graph. Speed is this, our velocity time graph is the derivative of our displacement time graph, and this is saying that our slope is getting bigger and bigger and bigger, which this replicates. All right. So then we got an object released from rest at time t equals 0, slides down a frictionless incline, a distance of 1 meter during the first second. Distance traveled in the time interval from 1 second to 2 seconds. This seems like it would be easy, but it's totally not. Or at least it's not until you get the hang of it. If it started, it was released from rest, so it had 0 velocity during time 0, and it has a constant acceleration, I believe. I will assume so. If it's down a frictionless incline, it would, unless it's like a weird incline. And it went 1 meter during the first second. So if we're going to have an average velocity of 1 meter per second during the first second, and it went from 0 to 2, remember, average is middle velocity occurring at the middle time. That means at 1 second, it must have been going double the displacement. Your average velocity is 1 meter per second, but that's got to be in between the two endpoints. 0 meters per second at the beginning, 2 meters per second at the end of 1 second. Anyway, so basically this must be 2. If you're having trouble with that, you can just do hey, V average is equal to V initial plus VF over 2. And if this is VF, and this is VI, and this is V average, you could do 0 plus 2 over, or sorry, you could rearrange this and solve. So we could rearrange VF equals 2V average minus V initial if you rearrange this sucker. And so that would be, our average velocity is 1 meter per second if it went 1 meter in 1 second. Basically it's 2 times 1 minus 0. So Hopefully that makes sense. Anyway, if you know it's, you also know if it accelerated from 0 to 2 meters per second in 1 second, that means it's accelerating at 2 meters per second squared. So if you want to know the distance traveled by the object in the time interval from 1 second to 2 seconds, you got a couple options. You can do either find the displacement at 2 seconds and then subtract the displacement at 1 second. Or my favorite way to do it is just to be like, hey, if I can also find the displacement by doing average velocity times time. So the time from 1 second to 2 seconds is just 1 second. And my average velocity, like if this continues from 1 to 2, and it's accelerating at 2 meters per second, it's going to go from 2 to 4. So on average, what's in the middle between 2 and 4? Your average velocity would be 3 meters per second. So my average velocity would be 3 meters per second. The time from 1 second to 2 seconds is 1 second. So it's just going to be 3 meters. Anyway, that's a long one. They get a lot easier the more you do them. But before then, it sucks. All right. So we got 2 people are in a boat capable of traveling a max of 5 kilometers per hour in still water and wish to cross a river, blah, 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 wide to the starting point. But if the speed of the water in the river is 5 kilometers per hour and they want to get straight across, they can't. The best they can do is hold their position if they aim their boat. Like if you got your river and you got your boat. That's a terrible boat, but whatever. If they're going 5 meters per second relative to the water, and the water is going 5 meters per second downstream, if they aim straight upriver, they will avoid being dragged down, but they won't go anywhere. As soon as they tilt up at all, they're not going to be completely canceling the river current, and they're going to move down a bit. And they can't recover that at all because they can't go faster than the river. Anyway, so it's just impossible. It is totally impossible. If they were at 5.01 meters per second, totally possible. But that is not an option. All right, vectors v1, v2 have equal magnitudes. The vector represents the velocity at times t1 and t2 respectively. Average acceleration of the object between t1 and t2 was basically the direction of the acceleration is always the same as the direction of the change in velocity. So you basically started off here and you ended up going like this. So if this is your start and this is your end velocity, it works same as displacement. Your change in velocity is in that direction. It'll be northwest. And anyway, your acceleration causes the change in velocity, and so obviously they have to have the same direction. So it would be north of west. All right, next we got a projectile fired from the surface of the Earth with a speed of 200 meters per second and an angle of 30 degrees above the horizontal. If the ground is level, what's the maximum height reached by the projectile? This one I shouldn't have to go over. Hopefully you remember it. Though maybe it's been a while. If you're going 200 meters per second and you want to know maximum height, really we only care about the vertical component because the horizontal component will have no effect. And if this is 30 degrees, what's sine 30? Sine 30 is 1/2. So our vertical component of our initial velocity is 100 meters per second. And 100 meters per second, we can just plug that into, what would we do? We would probably do Vf squared equals Vi squared plus 280. Vf squared equals Vi squared plus 2AD, everyone's favorite formula, or one of the excellent ones. Our final velocity, if it's going to its maximum height vertically, it'll slow down, stop. Of course, it's still got a bunch of horizontal velocity, but vertically, it'll stop. So our final velocity is 0. Our initial velocity is 100 plus 2. Keep in mind, our acceleration has to have the opposite sign from our velocity. Since I made the velocity up, positive, I've made up positive, acceleration has to be negative. And then t. Throw that in there. Basically, 100 squared, whatever that is. Oh, by the way, we can also use 10 here, so that'd make it easier to solve. We'd end up with 100 squared equals 20d. 100 squared divided by 20 would be 500. I believe, yes. Yes, it would. So, here we are, 500. There you are, not so bad. Very grade 11, 12-y. All right, let's do the next one into the calc. So particle moves along the x-axis with a non-constant acceleration described by a equals 12t. We want to know the position at 2 seconds. So if we have the acceleration and we want to go to position, we need to integrate it twice. Once, if we integrate it once, we do our integral of 12t once, that's going to be our velocity, and we're integrating with respect to time. We'll increase our exponent by 1. This is secretly a 1. So that would be a 2. And then we divide by our new exponent, so 6t squared. And then we need to integrate that again, as our displacement formula is the integral of our velocity formula, which is 6t squared d with respect to t. And so we increase our exponent by 1, so it'll be t to the third, and then divide by the new exponent. So it's 2t cubed. If we sub in t for 2, because we're interested in displacement at time equals 2 seconds. By the way, we should have had a constant here, which in this case would represent our initial velocity. But speed v is 0 when t equals 0, so we can just ignore that because that's 0. And then this would be our initial position, but position is 0 when t equals 0, so we can ignore that. Yeah, if they put in different numbers here, we just have to sub those in. So it's just 2t cubed, and then we got to sub in 2 seconds for t. So it's 2 times 2 cubed, which is 16. Whoop. And we're done that guy. We'll do 11 and maybe we'll cut it there for now. I'll break this into a series of videos, you lucky guys. Don't watch them all. Or if you do, hopefully you enjoy them. Sorry for being long. Catch you next time.